more people will show up. We have about the same people right now as on Wednesday. Yeah, I thought that grad students don't attend sports day, so I still taught. Well, part of it is I just forgot there was sports day. And yeah, I just thought it doesn't matter. Okay, so we started talking about Noether's theorem. Well, it's a combination of, so what we talked about on Wednesday, just to briefly recap, is that we finally wrote down the entire Lagrangian of QED. That's one way to summarize what we did. Right, so this is basically Maxwell, and this is the direct Lagrangian plus the coupling to electromagnetic fields, right, plus A mu, J mu term. Usually it's a minus, but yeah, anyway, so you have this term here that later on, when we do Feynman diagrams, we will discover that this is the vertex that is responsible for electromagnetic forces. Right? So these are either the flow of electrons or one electron and one anti-electron, and it couples to the photon. Right? And so this coupling will turn out to be very important. Without that, there are no forces between electrons. At least no classical forces between electrons. So we finished talking about this, and of course we know that now. That we now can conclude that the equations that come from varying the QED stands for quantum electrodynamics, right? Quantum and what we did was basically, we had varied this before. What we did was we varied this action, the Lagrangian, the action that came from this Lagrangian, and showed that it gave us the direct equation. And the direct equation itself is just this. So, in fact, we went further, right? And this is where the Noether current of where Noether's theorem comes from. So what we understood was that so even at the classical level, you would recognize that anytime you have a current, you need, for Maxwell's equations to be consistent, you need this guy to be conserved. Okay, so you take a divergence on the right-hand side, then this is an identity. The fact that it has to be zero is an identity because this is anti-symmetric. Okay. So you remember it's anti-symmetric, and you contract it to two derivatives, then this has to just cancel out. Okay. So anti-symmetric indices cancel with contracted with two derivatives has to cancel out, and as a result, it has to be that the current is conserved. But it turns out it's not conserved just as an identity like the left-hand side, but this is conserved. This is zero when J itself satisfies its equations of motion. Right, so J is not just some external, in a complete theory of electrodynamics, the current is not just some external thing that you just put in, right? In particular, for example, in this case, J is directly due to the flow of the electrons and positrons, giving you a current, electric current. And J itself must in fact obey, or rather the field building up J must itself obey the Dirac equation. And then you will find that it is in fact conserved. So what we discussed the last time was this statement, but from the perspective of symmetry. Okay, so here we're doing it from the level of the equations of motion. You see that it has to be conserved because otherwise the equations are not consistent, right? So left-hand side is an identity, but right-hand side is true because J itself has its own equations of motion to be satisfied. Okay? But what we did was we showed this statement. So this is 0 on the equations of motion through, this is last time, through the U1 symmetry obeyed by Dirac. So just a very brief recap. So here, by U1, we just mean psi is a complex spinor. So I can certainly take take it and do a rotation on the complex plane, right? And likewise, if you do this to psi, then you are obliged to also anti-rotate psi dagger, right? Because it's a complex conjugate of each other. But this guy, psi bar, so Dirac, if you write it out, it's actually psi dagger gamma 0, and then followed by IV slash minus m psi. So because of the presence of psi dagger and psi, this phase and that phase will cancel out, right? It will just cancel out. But if you vary this Lagrangian, so this is the part I won't do because that would take a lot of time, but we did this the last time. If you vary it, but use the equations of motion, in this case the Dirac equation, you will find that upon variation, you will get something like that. You would find that after you use the equations of motion, you will find something like that. Okay? If you vary the Lagrangian, use the equation, you'll find this. And so what we say is that therefore we view this psi bar gamma mu psi, which is a 4 vector. This is now the Noether current of U1 symmetry. Which means it's a conserved current that came out of a particular symmetry. Right? So let me just restate Noether's theorem again, because for the benefit of those who were not here. Noether's theorem tells us, and I think there's a couple of Noether's theorems, so I think it's supposed to be the first. I don't know what the second, or maybe there's even the third. I don't know what those are. But first says the following. Whenever a system has a continuous symmetry, so for example, in this case, the continuous symmetry is U1 parametrized by theta, right? So it's continuous because there's a theta there. Then there will be a corresponding conserved current. And this current we usually call locus current, right? Just as a tribute to Noether. Noether, I don't know my German. Noether, I think that's how you pronounce her name. But if anyone knows German correctly, Noether, I think. I should say this is usually a global symmetry that we, maybe I don't want to put it here, but usually for physics, it's a global symmetry, right? So in this case, as I showed you the last time, this statement is not the gauge invariance of this guy, because it is also gauge invariant, right? So this one is local, both locally and globally U1 symmetric. The local one, we call it a gauge symmetry, but that's not the one that gave us this. Right? So I want to emphasize that. Right? You don't see theta anywhere here because it cancels out, it drops out of the equations. So that's I think good to emphasize here. Okay. We also did chiral symmetry, but and then there's an anomaly there, but we won't do anomalies in this course because there won't be enough time. But so let me, in fact, today move on to scalars, okay, as further discussion of Noether's theorem. Yeah. Yeah, for those who came in, I taught on Wednesday because thinking that graduate students don't go to sports day. Do you go to sports day? No? Yeah. Anyway, I don't.
I was sick.
Yeah, I was. Were you here?
I mean, I was sick.
Oh, you were sick? Oh, okay. Are you better now?
Yeah.
Okay, good. Well, welcome back. Yeah.
Okay. Yeah, I have a question. So, what is the meaning of the physical meaning of the U1 transmission?
Yeah. So I think you asked me a similar question before, right? It's a little difficult to answer, right? In the sense that if you want to have an intuition for what is U1 symmetry, remember that I think we had this discussion before. It's a little bit difficult it is an abstract, right? You have a field, it's complex, and so you're allowed to think about this transformation. And so that's why when I motivated this, I appealed to first quantum mechanics, right? So if you remember, let me just say that briefly again. If you just think about quantum mechanics and about the wave function, then you know that we are always allowed to multiply the wave function by a phase, any phase we want, right? Because the probability of finding the particle is just always the square. So if you add, whether or not you add a phase, doesn't matter at all, right? So this is one way to motivate why we think about U1 symmetry, which is that we just say, okay, our field itself is usually not absolute, it's not an absolute observable. So let's think about rotating it. And in this case, it's certainly a symmetry, and particularly for Dirac, for fermions. The reason why it's usually a U1 symmetric is because when you construct Lagrangians for fermions, it would usually show up as bilinears. By bilinears, I just mean whenever there's a side dagger, there's usually a side. Because you want to sandwich some gamma matrices inside it to produce a space-time tensor, right? And then with the space-time tensor, you try to construct space-time scalars so that your Lagrangian is a scalar. So because of that, otherwise you can't have a standalone, four-component object, right? To form a scalar, you need to dot it into something. So that's why usually it will show up as a bilinear. Whenever there's a side dagger, there's a side. So U1 symmetry in particular is very common for fermionic theories. And so what we're doing, if you can think of it, is just simply working out this natural symmetry that can be both motivated by quantum mechanics and also just by virtue of the fact that because fermion bilinears are so common, let's see, what is a natural consequence of that, right? Yeah, so, but physically, if you by physically mean intuition, it gets a little abstract, right? So same thing with the standard model, right? Do you have a good intuition for, why SU3, or SU2 or whatever, right? It's what it is, right? But so in fact, in modern physics, in modern day physics, now people turn it around and say that symmetry, whether it's space-time symmetry or internal symmetry, is viewed as now more fundamental. Because even though it's more abstract, we realize that its importance, right? All the laws of nature were essentially discovered once people became familiar with these groups and tried to apply them to quantum field theory, right? So as you guys may have heard, the founders, the builders of this, what is now called the standard model of particle physics, they didn't know group theory, right? They learned it as they went along. So people like Salam and Weinberg, Gell-Mann, all these people, right? Gell-Mann is very famous for this SU3 model. But he didn't know his group theory when he was a toddler, right? He actually was told about it, and then he used it to do his theories. So that's why nowadays we realize it's important. So we turn it around and say, what are the symmetries in the theory, and from that you build whatever Lagrangian that are consistent with that symmetry. Yeah, so now that's what the status is, but of physics. But it is true, if you try to teach that to an undergraduate, right, you will have a hard time. The undergrad would stare at you and think you're from Mars or something like that, right? It's quite alien in that sense. Yeah, so when I teach quantum mechanics, I tell people, there's a similar story here, I guess, but for quantum mechanics, I tell people, I tell my students, if 100 years from now, we can teach quantum mechanics before we teach classical mechanics, then we can say we truly understand quantum mechanics, right? So there's, I think, a similar statement here, right? If there is a way to motivate these very, very fundamental symmetries in nature, right? U1, SU2, SU3, before we teach everything else, then I think that's the place where humanity has, reached a much deeper understanding of what we're doing, right? But we're not quite there yet, obviously. Yeah. Yes.
Do we always treat Lagrangian as a physical reality?
It depends on what you mean by that, right? It's certainly a very, very useful object that we use to construct our theories, right? If you really want, so we'll talk about this in a little bit when we quantize the theory, but if you really want, you can work, for example, with Hamiltonians instead of Lagrangians, right? So it's not something that is a unique way of doing physics, obviously. You can do, especially in quantum mechanics, right? You might view the Hamiltonian as more fundamental, right? Because it is the generator of time evolution that governs dynamics. But Lagrangians are the object that allow you to see the symmetries most easily, and this is why we do that. That's why we start very often from Lagrangians. Yeah.
Is Lagrangian always true? Real number?
Actually, for the direct guide that I'm writing it, the way I'm writing it, I don't think so. Actually, just take the complex conjugate of this. You will find that you will incur a. It is only real if I had integrated by parts the derivative. Yeah. So in this case, no. Yeah. So it's a little bit illegal what I'm doing here. I think strictly speaking, many books do it in an illegal way, which I am as well. But it's okay. We can get away with it in this case. Yeah. But yeah, strictly speaking, you should cook up a permission when you promote it to an operator, right? You should use a permission Hamiltonian, and that I think usually will give you a permission Lagrangian. Okay, so let's move on to scalar fields because we should continue our discussion on Noether's theorem. Yeah, so let's do scalar fields. I did Dirac because we have not even seen the Lagrangian yet until Wednesday. So I wanted to also use the opportunity to talk about the conserved current. But now that we have talked about it, we should also revisit the scalar field and talk about both internal and also space-time symmetries. So what I said about Noether's theorem applies both for internal and space-time symmetries, as you will see. So, in fact, let me give you an example of internal symmetry. Right? So U1 was kind of a natural symmetry for Dirac, but for scalar fields, you can also cook up internal symmetries. For example, this is an example of SOD symmetry. So let me write it down, and you can see it quite readily. So I have a kinetic term minus potential that only depends on phi I. Okay, so hopefully it's clear. If you view phi as basically a vector in field space, then this guy is basically, this guy and these guys are basically invariant. So this is my Lagrangian. Is invariant under the replacement phi I replaced with the rotation matrix contracted into phi j, right? Because this is basically a dot product. And remember the very definition of the rotation group is that it preserves the dot product. So it preserves both this guy and this guy. So in fact, now we can work out, for simplicity, because we know SO3 relatively well at this point, we can now work out what does it mean to generate the Noether current for an internal symmetry, in this case, the non-trivial SO3 group, right? So remember that for SO3, we have figured this out, that this is actually connector ij plus minus I theta, and then j hat. Mosquitoes, I really don't like mosquitoes. Why are there mosquitoes in the classroom? Anyway, ij phi j. Actually, it doesn't even need to be SO3, but any rotation we know can be parametrized as the rotation angle times the generator, and these generators are antisymmetric. I times the generator are basically antisymmetric matrices. Right? So j hat I times j hat ij are antisymmetric basis matrices. If you guys remember our discussion of rotational symmetry. All right. So what I'm doing here is I'm assuming that, I'm sorry, I'm just talking about the rotation matrices themselves. I'm just assuming that the rotation matrices involve very small angles. So if this is my rotation matrix, then the phi will go to phi I plus a small perturbation coming from this guy, minus I theta, and then j hat ij, and then ij phi j. Okay. Remember, we're talking about global, I should say, global SOT, meaning these are independent of space-time, right? If they do depend on space-time, then it would not, this guy would not be symmetric anymore, because the derivative will end up acting on this guy. And in fact, if you want it to be a local symmetry, this will be an example of a gauge scalar field theory as well, which is to say that you will go ahead and actually promote this guy into a covariant derivative, like the way we promoted it to promoted the derivative of the Dirac field to a gauge covariant derivative. But we won't do that here. We want to just study the Noether current that comes out of this global symmetry, right? So if this is how it transforms, this is not a space-time symmetry, so the derivative will also obviously transform in the same way, right? I'm not transforming the space-time at all, so obviously the way that the derivative transforms, would be the same, in the sense that you just take a derivative for this. But now we can work out what's going to happen, right? So I don't even need to be for the beginning. I don't even need to specialize to this Lagrangian. All I need to know is that this Lagrangian depends on Lagrangian depends on the derivatives and the field, and no higher derivatives, right? So this would mean that when I vary it, I just take the derivative with respect to the field and then multiply it by the variation. It's just a Taylor expansion, essentially, plus the derivative with respect to the derivative of the field. So now I need to give it an index, let's say partial alpha phi, and then I need to take the partial derivative of the variation of the field. Okay? Because I'm not touching the space-time indices, so I can just I'm just taking the variation of the derivative is basically the derivative of the variation. That would not be true for space-time symmetry, right? So we'll do that as well. It's not going to be the same for space-time symmetries, but we'll see how that works out. So now what I'm going to do is I'm going to rewrite this guy as minus partial L and then divergence of partial alpha phi. And you can probably guess why, because this is the Euler-Lagrange operator acting on L. And so if I write this term, I have to cancel it because it's not really here. So what I will have instead is I'll get plus partial alpha acting on the whole dl d alpha phi delta phi, right? So by writing it this way, this derivative acting on this guy will cancel this term, and then this acting on this will return you this original term, right? So again, these two terms gives you this. Okay. But now, as I said, this is the Euler-Lagrange. This is Euler-Lagrange. So therefore it's 0. Right. So remember that the equations of motion come from demanding that the action now it's time to talk about space-time symmetries. Yeah, so for your next homework, you will also be doing a problem involving U1 symmetry for scalar fields. And so I told the Wednesday class that that is going to be an example of an electrically charged scalar field, because there you would work out the what is called the abelian Higgs model. And so there are a few things that you will learn about that. One is the U1 symmetry, and that U1 symmetry is both at the global and local level. And you can use the gauge symmetry to basically get rid of the phase of the scalar field, the complex phase of the scalar field. And then after that, you will learn something about spontaneous, what is called spontaneous symmetry breaking. It's the simplest example of spontaneous symmetry breaking I know about. And so let me just say that in case you guys can benefit from it. Right? So this is gauge invariant. When you add a mass term, it's no longer gauge invariant, because when you shift A by a gradient, this remains invariant, but this doesn't remain invariant. But actually, it depends on where it comes from. Okay, so it depends on where it comes from. Appearances can be deceiving. So what you will discover is that the abelian Higgs model is the simplest example where you can impart a mass to the gauge field without actually breaking the U1 symmetry. And so there's still electromagnetism, but in that context, it's actually a model for a particular type of superconductors, right? The one, I always forget whether it's type 2, I think it's type 2, that exhibits the Meissner effect. And I believe the mass there is just the skin depth of the magnetic field. But what you will work out is also based on that model. You will not be able to read off the mass right away, but you have to do some work to figure out what the mass of the photon is. Right? So the abelian Higgs model looks something like this. Minus, there's a potential, and then of course there's the usual Maxwell. So this potential is crucial for giving a mass to the photon through the kinetic term, right? So you will discover for yourself what that is. But I want to mention this because it is very much tied to this discussion of internal symmetries. I don't think it's this one work, it's the next one, I think. Anyway, so now let's talk about space-time symmetries. And probably I'll only have time to talk about translation first. So the first thing is translations. By space-time, I really mean conserved, right? But translations first. So what translations mean is that if I'm in the space-time location x mu, I will go to x mu plus a mu, right? Where this is constant. So it's just a shift in my, a linear shift in my location. So the way we usually build our Lagrangian, we usually build it as a scalar, right? We usually build it as a space-time scalar. So the Lagrangian itself will go to itself plus a. The space-time location, because it's a scalar, will just go to itself plus a, which is the location x. But for small a, you can expand the Lagrangian, right? Because it's a scalar, so this would just be a sigma partial sigma L of x. Okay. So that's how the Lagrangian would transform. But on the other hand, for example, if you're dealing with scalar fields again, then let's think about what the scalar field would do. Okay, so again, the scalar field itself will go to itself plus a sigma partial sigma phi of x. Exactly because the scalar field, like the Lagrangian, is a space-time scalar, right? So phi of x will go to phi of x plus a, and therefore you can just expand it like the way we expanded for the Lagrangian. So, and because the shift doesn't affect the derivative, so the derivative will also behave in the same way. So if you want, I can add an index to alpha, alpha, alpha. Okay. So now, if you now vary this guy, you will get the following, right? You get it back itself, plus, now you get a derivative with respect to d phi, plus d alpha phi, and this is in fact the variation of, this is the variation of the derivative, right? And this guy is the variation of the field itself, okay? So what is the variation of the derivative? It's given by this guy, a sigma partial alpha phi, and then plus the L d phi, and then d phi, right? So it will be a sigma partial sigma acting on phi. Again, this is dl d phi, d phi, dl d phi, and then this is delta of d phi. Okay? And then of course there are higher order terms, but we'll only keep it to first order. So what it tells you is that whatever this changes, it must in fact be equal to this, right? So this in fact must be equal to this, because this is delta L, and so is this guy. This is also delta L, and so obviously they must be equal. So what is the consequence of that? Okay, the consequence of that is the following. Again, I am going to, for the derivative term, I'm going to write this guy, basically integrate by parts, but write it as a, and then arrange it into a Noether current looking thing. Okay, so let me just write that down first. So let me write this guy down first. Let me change that notation to beta. A beta partial beta dl. And actually let me write it in the following way, just to save some time. Let me write it as partial alpha, and then Kronecker alpha beta. Oops, I'm sorry. I mean alpha beta, and then a beta L. Okay. And you can see that because a is a constant, this will just become partial beta acting on L with a dotted into it. Right. So this term is just this term over here. And this is equals to, let me do this guy here. Actually, let me write this guy down. Yeah, equals to a beta d L d phi d beta phi minus d alpha dl d alpha phi. And actually I'm going to write it in this way. I'm going to bracket it out and write this down as partial beta phi. Right? So again, this term is this term here. This term plus partial alpha A beta partial alpha dl d alpha phi d beta. These two terms is this term here, okay? Because when this is acting on this, it will cancel this term. And then when this guy is acting on this, it recovers this term, okay? And now you see why I do this, because this guy is 0 by the equations of motion. Okay, that's the Euler-Lagrange equations. And now I can put them together. So I can write them as A beta and then partial alpha acting on this whole thing. dl d alpha phi d beta phi. And then if I move this over here, I get minus Kronecker beta alpha Lagrangian. This whole thing must be 0 when the phi itself is evaluated on its equations of motion. Right? In other words, if phi is a solution, then this has to be conserved. Now, in this case, we have a constant current, constant vector. So because it's arbitrary, the whole thing must be conserved no matter what A is. So therefore, the whole thing here, which has in fact two indices, J, alpha, beta, both are space-time indices, is in fact conserved without the A. And let's do a simple example. So for example, for the canonical, what usually people call the canonical scale, which is kinetic energy minus potential energy, then you can easily calculate what the current looks like. So dl alpha always gives you partial alpha phi, and then multiplied by d beta minus Kronecker alpha beta times the Lagrangian, which is just 1/2 partial phi squared minus v. Okay. So those of you who have taken GR, general relativity, would recognize that this is actually the stress tensor of this, actually, let me write down the full name. Is the energy momentum shear stress tensor. Okay, it's not a coincidence. Just think about what we have been doing. What we are doing is basically we are working out the Noether current that arises from space-time translation symmetry. Right? This guy is conserved directly because of the space-time translation symmetry enjoyed by this theory. Right? The Lagrangian is a scalar under translation. The field is a scalar under. So therefore, this is a consequence of that. So time translation symmetry, remember, gives you energy conservation. Space translation symmetry gives you momentum, linear momentum conservation. So essentially, this object here, the matrix here, right? So it's a matrix because alpha beta runs from 0 to 3. So this 4x4 matrix essentially are the components of energy, momentum, and what we call shear and stress that directly comes from the conserved quantities that we associate with space-time translation symmetry, right? So why do we call it energy? energy is the conserved quantity associated with time translation symmetry. Linear momentum is also the conserved quantity related to space translation symmetry. And so we remember that when we talked about the conservation of current for the first time, we associated that with the conservation of mass density or some substance, whatever substance it is, right? So in this case, we have basically 4 different substances, which is why we have 4 different betas. Instead of having one row, we have one row for energy, one row for the first component of momentum, one for the second component of linear momentum, and then the third component of linear momentum. And so shear and stress, in fact, is the off-diagonal and diagonal components that correspond to linear, the conserved current for linear momentum. Right? Yeah, so let me just write down shear and stress. These are the off-diagonal components and the diagonal components corresponding to the Noether current of space translation symmetry. Okay. So shear, by the way, means that if I exert a force like that, and if there's a shear, it means that the layers of the material will start sliding off each other. Pressure means that if I push on it, and if the material is not strong enough, it will just give way, right? So the pressure is basically force per unit area orthogonal to the surface. Shear is a little bit more difficult to define, but roughly speaking, it's basically the force parallel to it. So it will start to shear off, as the name suggests, shear off the layers of the material if it doesn't have. But again, it can be related to the off-diagonal components of off-diagonal and diagonal components of the conserved Noether current of spatial translation symmetry. Yeah. So next time, I will talk more about this because we only did space-time translations. There's still Lorentz and rotation, right? And basically the Lorentz transformations. So what we'll discover is that there's a subtlety especially when you go to higher spin fields, you will discover that for scalars, Lorentz transformations will generate angular momentum, orbital angular momentum. But when you go to higher spin fields, you will discover that this stress tensor, or the JAV that you generate, will no longer be exactly the stress tensor that you get from GR. But it will be slightly different, and we'll talk about why that is the case. Okay. Any questions for me?
I just want to check. So the Noether current for space-time is nothing but energy momentum tensor contract with Killing vector.
In this case, in this case you can think of this as a Killing vector, right? Because it's just a derivative with respect to some direction. Yeah, but in general, you will find that, like I just said, for higher spin fields, so vector fields, Dirac fields, and so on, actually it turns out that it's not exactly the same thing. Yeah, so and that is a subtlety. You will discover, so I'll tell you the problem. So the problem is that when you try to generate the same thing, as you do for, say, photons, right? We just wrote down photons. You will discover that this guy is neither gauge invariant nor symmetric. And so you might wonder, so what, right? So in particular, if this thing is not symmetric, and you force the interpretation that it's a sure that you have a stress tensor, then what you will discover is that you can generate a finite amount of torque on an infinitesimal volume. Right? If your stress tensor were not symmetric, you will be able to generate a finite torque on an infinitesimal volume. So something very unphysical, right? And so the answer to your question is only partially, for some reason. It's not quite the case for higher spin. Yeah, and we'll talk about why the next time. Yeah.
I want to ask about internal symmetry. So could we regard different value of index capital I as different particles?
Yes, when you quantize them, basically it means that the field, let's say you are doing an SOD invariant scalar field, then yes, after you quantize it, you will discover that you can just associate a fluctuation for each phi I, right? So if I runs from 1 to D, then you have D different scalar particles. That's exactly right. Yeah, different species of the same scalar particle. That's one way to put it. Yeah. Yeah. That's kind of what gluons are like also, right? Gluons are SU3, and SU3 has 8 generators. So you also have 8 different gluons, basically. Yeah.
So does this mean that the SOD, we mentioned that it can transform one particle to another one?
If you allow it to interact, yes, that's exactly right.
Yeah.
So in particular, then that's in fact how you test it experimentally, where you test whether the particle interactions respect the SOD invariance, right? So there should be some consequence of that. And also how it interacts with other particles as well. Yeah, that's exactly right. Yeah. Okay, see you guys next week.